And we're back with another video lecture. In this lecture, we're going to talk about intervals, power sets, and introduce the idea of a function. So let's jump right into it. So in mathematics, we often use special sets called intervals. You've used these for most of your mathematical career. So what is an interval? Well, there's four flavors of intervals, so to speak. So an interval a comma b with square brackets is this set, the set of all x and u, such that x is greater than or equal to a and x is less than or equal to b. So here u will depend on the context. It could be real numbers, it could be integers, it could be rational numbers. Those are the most common sets that we use. But technically you could define an interval of, any objects as long as this less than or equal to sign is well defined. So now what do we call this interval? Well, this is our friend the closed interval. Next, we have the interval parentheses a comma b closed bracket. This is the set of all elements x and u such that x is greater than a and x is less than or equal to b. Our next friend, the interval bracket a comma b parentheses, that's going to be the set of all x and u such that a is less than or equal to x and x is less than b. And finally, our friend, the interval parentheses a comma b close parentheses, will be the set of all x and u such that x is greater than a and x is less than b. So this last interval has a name. It's called the open interval. These two other intervals you could call half open or half closed if you want, but we're not going to give them any particular name here. So again, u is most commonly taken to be z, q, or r, but again, you can use any set of objects as long as these operators are defined for the objects that you're using. So those are the four flavors of intervals. Now, one important thing to note here, the null set is an interval. Explicitly, if a is equal to b, then this interval here is going to be the empty set. So now let's look at an example. Let a, b, c, and d be real numbers such that c is less than a, which is less than d, which is less than b. Write the intersection of this interval and this interval as an interval. So let's go over to our good friend Mr. Paint. Okay. A key thing to note for this problem is that I simply told you to write this as an interval. I didn't ask for any particular justification that it can be written as this interval. So how could I do this? Well, let's draw a number line. And on this number line, let's indicate where a, b, and c are. So I know that c is the smallest of these objects, so c is sitting here. Next, I have a. Next, I have d. And next, I have b. So I know a is not equal to c, or say d is not equal to a, etc., because I have less than signs here. So now this interval from a to b, explicitly, this will include all of the elements, including the endpoints here. And this interval c to d will be open here and open here. So if I go to intersect between these two, the intersection will simply be all the stuff in this region. So to answer this question, the intersection of these two intervals written as an interval would simply be the interval with square bracket a, comma, d, round bracket. Now, if I were to ask you to say prove or disprove that something is an interval on, say, maybe homework question 2, perhaps, then using a number line like this could help you to get a grasp of what you need to do to either prove it or to find a counterexample, but it's not sufficient for a proof. For a proof, you'd need to explicitly appeal to these definitions of the interval. So explicitly, if you wanted to show something is an interval, you need to show that it can be written in one of these forms. So now let's continue. The power set. So what is the power set? Well, remember our friend the set of all sets? He's back, but with a restriction. So explicitly, the power set of a set A is the set of all subsets of A. So we can rewrite this as P of A with the curly P is equal to the set of all X such that X is an element of A. Notationally, we can write that the power set of A, denoted by this curly P of A, is simply the set of all sets such that that set is a subset of A. So now with this restriction that we're talking about X as a subset of A, we avoid the issues that can happen when, say, trying to consider the set of all sets. So while power sets are, quote, powerful, they're not, so what are power sets good for? Well, going beyond this course, being able to talk about the set of all subsets of a given set is useful for proving lots of theorems. It's useful in a lot of counting arguments. It's useful when, say, trying to talk about various properties of infinite sets. Power sets also are very useful to prove that certain sets exist or can't exist. So it's a pretty versatile tool overall, so just keep that in mind. Okay, so now that we have this definition, let's go through some examples. The power set of the empty set. So take a minute, think about this, see what you think it is. Okay, so now what are all the subsets of the empty set? Well, the only thing is the empty set. What about the power set of the power set of the empty set? So pause the video and think about this for a bit. Well, the power set of the power set of the empty set is simply going to be the power set of this set containing the empty set. And now, what are the subsets of this? Well, it has two subsets. The null set is always a subset of any set, so the null set is going to be in the power set of this. And this set contains the null set, therefore the power set of this set also contains the set that contains the null set. I just said null set a whole lot of times, but you can continue this process indefinitely. For instance, the power set of the power set of the power set of the null set will be, well, let's digress and take a look at it. Well, here's what it would look like, and explicitly I already computed what this set here was. So now I can rewrite this as saying that this will simply be the power set of the set that we found just a minute ago. So explicitly this. So now what are the subsets of this? So trivially we have the null set because the null set is a subset of any set. So next I have the set that contains the null set, and then I have the set that contains the set that contains the null set. And finally I have the set that contains the null set and the set that contains the null set. So explicitly writing that out to make it a lot more clear, I have this set here. So this would be the power set of this set. Okay, back to our main lecture. Let's look at another example. What is the power set of 1? Well, take a moment and think about what this would be on your own. Okay, so the power set of the set that contains 1 will simply be the null set and the set that contains 1. Next, the power set of the set that contains 1 and 2, what would this be? This would be the set that contains the null set, the set that contains 1, the set that contains 2, and the set that contains both 1 and 2. So again, this is similar to what I had here, where I have nothing, the set that contains the first thing, set that contains the second thing, and the set that contains both. But within this example, it's a little less confusing because I don't have null sets everywhere. So finally, one more example. What is the power set of the integers? Well, the integers are infinitely large, so the power set of the integers would also be infinitely large, so we can't write it out, but we do know this is going to be something really big. It has at least infinitely many things in it, right? That's infinity is a big, quote, number, and we'll quantify that a little bit later. But we'll talk about this idea later when I start talking about cardinalities and infinity next week. So just a little teaser for that topic. So now one thing to note that's a common error made by students. The elements of the power set are sets. So don't forget this and make sure you use the right notation at the right places. So now that we've introduced a new thing that we can do to sets, let's talk about its properties. For sets A, B, and C, the following hold. So A is an element of the power set of B if and only if A is a subset of B. So explicitly, this is saying that A is a set in the power set of the set B if and only if A as a set is a subset of B. Okay, next, the null set is always going to be an element of the power set of A no matter what A is. The null set is always a subset of any given set, therefore it's going to be in the power set. A is in the power set of A no matter what A is. For any given set A is a subset of itself, therefore this has to be true. Next, if A is a subset of B, well, that implies that the power set of A will be a subset of the power set of B. Well, why is this true? Well, I'll give a kind of a more detailed argument for why this is true later, so let's skip that for now. If A is in the power set of C, then A minus C is in the power set of C. Well, why would this be true? Well, the power set of C contains all of the subsets of C, And if A is a subset of C, then C minus A would also have to be a subset of C. That is essentially the argument that you need to make here, but you can, of course, make that a lot more formal than what I just said. So next, if A is an element of the power set of C and B is an element of the power set of C, then the following are elements of the power set of C: the intersection, the union, and the difference going both ways. So why would this necessarily be true? Well, if you just think about the definition of the power set of C and the definition of these operations, it falls out pretty much immediately by definition. A good exercise would be to try to show one of these is true. Essentially unpack all the definitions and kind of zip them back up. Okay, so as promised, let's prove the fourth one of these statements. So explicitly this one here. So let A be a subset of B. And now my goal is to show that the power set of A is a subset of the power set of B. How am I going to do this? Well, I'm going to pick an arbitrary element of this and then show that it also has to be in here. So let's do this. So let X be an element of the power set of A. Well, what does this mean? By the definition of the power set, this means that X is a subset of A. Okay, so how does this help me from here? Well, I know A is a subset of B. So since X is a subset of A, X has to be a subset of B. So now that X is a subset of B, by the definition of the power set, X will have to be in the power set of B. So the proofs for the rest of these statements are very similar to this type of an argument. Just unpack the definitions and then repack them back up where you need to. A good exercise would be to prove the rest of these statements. And again, you could see any of these on, say, like a midterm or a final where I ask you to prove them. So now we've talked about several properties of sets, so let's do a meme recap. So here you see the various operations and special sets that we've talked about. So let's just briefly compare and contrast what the different operators do. So the union, it brings people together, it's outgoing, he's large and in charge, and always says yes. The intersection, he's great at finding common ground, he's quite focused, he sometimes excludes people. Yeah, he probably has a LinkedIn account. The superset, he always thinks that he's better than you, he's always a little bit extra, looks at memes all day, and uses big words to sound smarter. Subset, shy and insecure, kinda unoriginal, super cute but down to earth. Empty set, gets jealous all the time, he's a total nihilist. Super edgy and listens to Bon Iver. The power set, he's Mr. Know-It-All. The leader of the group, always wearing a new outfit and quite successful. So I found this online. I don't know if it'll help you at all, but it's a pretty good summary of what the different operations do, even though it doesn't explicitly state the definitions of the operations. Okay, so now back to actual math. Let's talk about what a function is. A function from a set X to a set Y is a relation. F is a subset of X times Y, such that every X in X appears in exactly one ordered pair of F. So what is this really telling us? Well, this is telling us that all the stuff that we talked about relations before, well, they apply to functions. A function is a particular type of a relation. So let's look at an example of what a function is. So if X is, say, the collection of X1 through X5, and Y is the collection, say, Y1 to Y5, then F, given by this expression here, so here I have the ordered paired X1, Y1, X2, Y2, X3, Y3, X4, Y3, and X5, Y3. This is a function because each one of these elements here appear in exactly one ordered pair in this collection. So this would be a function. On the other hand, if I change these last two collections to be X3, Y4 and X3, Y5, this would not be a function because X3 appears in 3 ordered pairs. So if you tie this back to your old definition of function that you've probably seen, for even any given value X in X, there is exactly one value Y in Y that X is associated with. So speaking of old definition of functions, oftentimes we'll write a function f in a few different ways. One, we could say f maps from X to Y, or we could say X is mapped to Y by f. I won't be using this notation. I just wanted to throw it out there in case you ever see it. And if we want to be explicit in how f is acting on the elements of X, we can write f is a function from X to Y such that X is mapped to f of X. So here, this f of X can be any of the functions you've ever seen before. It's just representing some function that you can plug in there. So now, under this new notation, I can give an equivalent definition of a function to this first definition that you may have seen before. So explicitly, a function from a set x to a set y is a relation f mapping x into y, such that for every x in x, there is a unique value f of x in y. So again, this is just saying that for any given element x in x, there is a unique or a single value f of x in y. So let's look at the example that I gave before within our new nomenclature. So recall that f given by this function here is a function, and under our new notation, I can rewrite this f as little f mapping from x to y. Here, x will simply be the set x1 up to x5, and y is going to be the set y1 up to y5. And under our new notation, this function takes x sub I, and if I is equal to 1 or 2, it maps that to y sub I, and if I is equal to 3, 4, or 5, it maps that to y sub 3. So now, some of this can be a little bit daunting when you first see it, so let's look at a graphic for what I really mean by a function from x to y to try to make this a bit more concrete. So explicitly, I have my friend the set x over here, and I have my frenemy the set y over here. So the function is taking elements of x and sending them to some elements in y. So in particular, this function f, or this function f here, what is it doing? Well, it takes x1 and it sends it to y1. It takes x2 and it sends it to y2. It takes x3, x4, and x5, and it sends all of them to y3. So this is graphically what this function f is doing. Now, explicitly, this is a function because for any given value x, I send it to something over in y and only one thing. I don't fragment these values. For instance, x3 doesn't go to y2 or y3. It goes to a distinct, unique value. Okay, so now that I've introduced the basic idea of a function, and you should have potentially seen this graphic before, let's talk about some terminology. If f is a function from x to y, then the set x is called the domain of f, and we write x is equal to dom of f. Secondly, y is called the codomain of f, and we write that y is equal to cod of f. So one point of potential confusion, do not confuse this with the fish. It is the codomain, it's not a fish. Okay, next, for any x in x, so for any element over here, we say that x is the pre-image of f of x in y. So we know that f sends every element in this set x to some element over here. Thus, if I consider some point in the set y over here such that something gets mapped to it, I can then say that x is the pre-image of that thing. So that's why I'm a bit careful here where I say this f of x is an element of y. So if I go back 1 second, I noticed here this y4 and y5 don't have x's associated to them. So I need to be careful and explicitly say f of x is an element of y instead of saying y is an element of y. Next, for any y and y with y is equal to f of x, we call y the image of x. So note again, for any given y, there is not always such an x, simply because of the example that I gave before. So for the note card version of these last 2 points, for any given x in x, that value of x is the pre-image of f of x and y, because f has to map x to something in y. But for any y and y isn't always going to be the image of some element x. It will only be the image if y is equal to f of x for some value of x. So next, the range of a function denoted by range of f, or f of x with capital X denoting all of the elements in the subset, is the set of all images. So explicitly, the range is the collection of all things that the elements of x map to. And do note that the range will be a subset of y, or explicitly, the range is a subset of the codomain. So writing this out, the range is the set of all y and y such that there exists an x and x such that f of x is equal to y. Or in other words, the range is the set of all y in the codomain of f such that there exists an x in the domain of f such that x is equal to y. So the second version is just using our nomenclature in these first 2 bullet points. So we've now just introduced a lot of new words. let's kind of examine what these mean graphically to get a better idea of what these things really are and kind of how they interact with each other. So if f is a function from x to y, then graphically we have this guy here. This is the plot that I showed previously. So here we can ask, what is the domain, what is the range, what's the codomain, what's an image of something, and what is the preimage of something. So firstly, the domain of f will simply be x. It's what I'm mapping from. The codomain of f will be y. It's what I'm mapping to. Next, what if I wanted to know what the preimage of y3 is? Well, all of these values here, x1 through x3, are all going to be the preimage of y3. Next, I can ask, well, what's the image of x2? Well, x2 maps to y3, so this would be the image of x2. So next I can ask, what is the range of f? Well, the range of f will be all of the elements over here in y, such that there's something over here in x, such that f maps that point to the value in y. So explicitly, for y1, y2, and y3, there exists a value of x and x, such that f of x is equal to these values. Therefore, the range of f, or f of x, is simply going to be these 3 points here. So this figure here summarizes an example of the domain, codomain, etc. for one function, and it's probably a good idea to keep this image in mind when thinking about these various objects. So next, I can ask a question. Given a function, can I undo it? So you've worked with functions before. Inverse functions are nice. In particular, inverse functions allow us to solve for things and do lots of handy-dandy useful things. So given some function, can we find an inverse function or can we undo it? Sometimes, sometimes not. That's what we talk about next lecture. Now that we've introduced all of this stuff, let's go through some examples. Find the domain, codomain, range, and preimage of 1 and image of 0 for the function f, mapping from the non-negative real numbers to the real numbers defined by x is equal to x squared. So first, I really need to ask myself, is this a function? The answer to that is yes. So for any given value of x, x squared has a unique value, so I'm a function. Therefore, all of this stuff makes sense. Okay, so what would the domain be? So pause the video, think about it for a second. Okay, so the domain is simply going to be the set that I'm mapping from. So explicitly, the domain will be this set. What about the codomain? So take a second, think about it. Well, the codomain is just the set of things that I'm mapping to, so that's going to be the whole real numbers. What about the range? So take a second, think about this. The range is a subset of the codomain that are the elements of the codomain that I'm actually mapping to. Well, for this particular function, I take a real number and I square it. When I square a non-negative real number, I simply end up with a non-negative real number. Therefore, the range in this case isn't going to be r, it's going to be r0 plus. So again, this is being treated as the subset of this, not the domain over here. Okay, next, what's the preimage of 1? So to answer this question, I need to answer the question, what maps to 1? Well, here, this function takes some element x and maps it to x squared. So to answer the question, what maps to 1, I need to solve the equation 1 is equal to x squared. So we know this has two solutions. It's plus or minus 1. But here's where I need to be a bit cautious. My domain of f of x is simply the non-negative real numbers. So only 1 is in the domain of f. So the preimage of 1 is simply going to be 1. Next, what's the image of 0? This is asking, what does 0 map to? Well, when I plug 0 into this x squared function, what comes out? 0. So the image of 0 will simply be 0. Okay, one more example. Consider the function f mapping from r to r, given by x is mapped to x squared. So this function is different than the first function in that I'm now mapping from all of the real numbers instead of this restricted domain. So here, the domain will simply be r. The codomain will simply be r, and the range, again, is simply going to be the non-negative real numbers. Okay, so before we end this lecture, let's talk about an application of a function. So a charger is something all of you use on realistically a daily basis, and what does a charger do? I have some voltage that comes in from the wall, and it goes through the charger, and I have a voltage that comes out. That's not all that a charger explicitly does. I often convert from AC to DC, that type of thing. But with this simple model, a charger takes a voltage in and then outputs an output voltage. This can be modeled by a relation between the input voltages and the output voltages. Again, order matters because I have a different result when I flip the input and output voltages. So explicitly, voltage out is equal to F of voltage in, and this function F relates the output voltage to the input voltage. So in practice, this will be a function instead of just a relation, simply because for any given input voltage, I only have one output voltage, given that the charger is not broken. If I have different output voltage depending on the input voltage, something's probably wrong. So now, a very important question that I could ask for practical cases is, can I find the input voltage as a function of the output voltage? For instance, say if I want the output voltage to be within a particular range of values to keep, say, my laptop or cell phone from blowing up, then I might want to write the input voltages as a function of the output voltages. Therefore, I can just plug in the output voltage range that I want, and from there deduce what my input voltage range should be. So the answer to this question of can we find this is sometimes. It depends on if the function has certain properties. And those properties are what we're going to talk about in the next lecture. So explicitly, sometimes, see you next lecture. So we'll end you with some assigned reading. So read pages 40 through 43. And I will see you next lecture.